In this video, we're going to talk about functional independence, also known as cohesion and coupling. As a reminder, cohesion is the degree to which a module performs one and only one function. And coupling is the degree to which a module is connected to other modules in the system. In general, you want components that are strongly cohesive but loosely coupled. However, these can often be opposing properties. Since strong cohesion means that a component does only one thing, a system with strongly cohesive components will probably have a lot of them, meaning that there's probably a lot of coupling in the system. Alternatively, one reason that a system could have loose coupling is that it only has a few components. The fewer components, the more likely it is that those components have to do more than one thing, and hence are not strongly cohesive. Here are Martin's package cohesion principles. These principles tell us what kind of components belong together in a package. The release-reuse equivalency principle says that the granule of reuse is the granule of release, meaning that you should group together components in the same package if you plan to officially release them together. Releasing means versioning, like version 1.0, version 1.1, and so on. But it's not enough just to group all the components in a single package, because the last principle, the component reuse principle, says that you should not group components if they are not reused together. If you have developers that are reusing your components in their own systems, they may not want to use your components if they add a lot of unnecessary bulk to the system. The middle principle here is the odd one out. It says that you should group components based on whether they change together. The two reuse principles benefit those who reuse your components, while the principle based on change benefits those who are maintaining your system. Sometimes you have to decide how to strike a balance between these competing needs. These are Martin's package coupling principles. In introducing these principles, here's what Martin has to say. Applications tend to be large networks of interrelated packages. The rules that govern these interrelationships are some of the most important rules in object-oriented architecture. The first rule here is very straightforward. Dependencies between packages must not form cycles. By the transitive property, if A is dependent on B and B is dependent on C, then A is dependent on C. If you have a cycle in your dependency structure, it essentially means that every package in that cycle is dependent on every other package in that cycle, which in turn means that someone trying to maintain and reason about a single package in the cycle is now going to have to reason about all the packages in that cycle. Before we move on here, I should say that it threw me off a bit when Martin started talking about dependency between packages rather than dependency between components. Now, considering that a component may be a collection of related classes, which is also the definition of package, I don't think we should put too much emphasis on this distinction. Everything Martin says here about coupling between packages applies to coupling between components, even components that consist of a single class. Okay, the second principle here says that you should depend in the direction of stability. This means that if you depend on a package or a component, it's better if it's a stable component, meaning it's better if the component will not change that much. Now the question, what kinds of components tend not to change a lot, is answered in the third principle here, abstract components. And this is similar to what we saw when we talked about component reasoning. You depend on the abstractions, and those tend not to change since they only contain the essential information to use them. The implementations, or concretions, on the other hand, are things that do change, so you want to minimize the dependency on those. Taken together, principles 2 and 3 really look like the dependency inversion principle as applied to packages. Cohesion is the single-mindedness of a module. A component should only contain attributes and operations that are closely related to one another. The three types of cohesion that we're going to look at here are functional cohesion, layer cohesion, and communicational cohesion. Functional cohesion is the most straightforward. Here it is applied to functions inside of a class, but the notion scales up to classes and packages as well. In this example, the camera class on the left has 5 methods. One that determines the camera's type, one that moves the camera around the floor view, one that displays the camera ID, one that displays the camera view, and one that displays the zoom. In the camera class on the right, we consolidated the last 3 methods into a single method. Obviously, this violates functional cohesion because we have one method performing 3 different tasks. But what's really so wrong about this? Please pause the video and see if you can think of some problems that might arise from consolidating these 3 methods. Ready? Well, I think the biggest problem here is that common theme that continues to appear everywhere in this course. And that is the theme of change. Software will change, and if we need to change the display zoom portion of the display camera function for any reason, then we risk introducing bugs into the display ID and the display view portions of that same method. If we keep all those methods separate, then we don't have that problem. The second kind of cohesion is layer cohesion. A higher layer in the system can access a lower layer, but not the other way around. Now, this seems reminiscent of Martin's principle that package dependencies should not form cycles. If you find that you cannot possibly avoid a cycle in your package dependencies, then you're effectively saying that all of your packages are related to one another. And if that's true, they should therefore be grouped into one cohesive package. The third type of cohesion is communicational cohesion. The main idea behind this type of cohesion is that all operations that access the same data are defined within the same component. The slide gives an example of a student record class, but really, this is the fundamental principle behind object-oriented programming in general, that data and the operations that manipulate that data are encapsulated into a single container, the class. Coupling is a quantitative measure of the degree to which classes or components are connected to each other. We're going to talk about 3 kinds of coupling. Content coupling is very bad and should always be avoided because it breaks information hiding. Common coupling is the sharing of global data, and while you should use caution when doing this, there are times when it makes sense in the context of your overall system architecture. And then there are several kinds of coupling which are routine in object-oriented languages. For example, any kind of dependency on another class reveals a kind of coupling. These kinds of coupling are necessary for a program to function. Otherwise, there would be no communication between the components. But in general, you should be aware that it's occurring. And if you see the import section of your class growing out of control, perhaps it's time for a bit of refactoring. Content coupling is the most serious type of coupling. It occurs when one component surreptitiously modifies the data that is internal to another component, and it therefore breaks information hiding. The best way to understand this is to look at a class where it occurs. Here we have a student record class. It has two private fields, name and quiz scores. Name is a string and quiz scores is an array of integers. There are three methods. One of them returns the name, another returns an individual quiz score, and the last returns all the quiz scores. But there's a problem here. In fact, go ahead and pause the video and see if you can tell me what the problem is with this class. Ready? First, let me tell you where the problem is not. It's not with the private data, it's not with the getName method, and it's not even with the getQuizScore method. The problem is with the getAllQuizScores method. But let's go through all of these methods one at a time so that it becomes obvious what's happening. First of all, notice that the fields are private, as they should be. That means that we don't want to give clients direct access to them. And specifically, if you look at all the methods here, they're all get accessors, which is a pretty good indication that the information in this class is meant to be read-only. The getName method returns the name, which has type string. In Java, the string type is immutable. So even though the client has access to the actual string object that represents the name, that object is immutable, meaning it cannot be modified. Now let's look at the getQuizScore. This returns an integer score for a specific quiz. In Java, an integer is a primitive type, which means that the client is getting a copy of the score. So again, the client can't change anything. The problem arises with getAllQuizScores. The class is returning an array, but it's not just any array. It's returning the same array that is used to represent the quiz scores in the object. The reason this is bad is that arrays in Java are mutable. They are changeable. If you give someone access to an array in Java, they have the ability to modify all the cells in that array. Therefore, in the case of this class, data that was meant to be private can be modified easily by the client after he or she calls getAllQuizScores. Note that one way of getting around this problem would be to return a copy of the array. The client could still modify the copy of the array, but the original array would not be changed. Common coupling occurs when components use the same global variable. In this case, the variable environment.setup is used by both classes. This example probably indicates an especially troubling instance of this type of coupling because the classes are in entirely different packages. The example would be less problematic if the classes that shared a global variable were in the same package. Finally, routine coupling occurs all the time in object-oriented languages, including import coupling, where you are simply importing another component, type use coupling, where you are declaring a variable using a type that you've imported, and routine call coupling, where you're calling a method from a type you've imported. The common thread is that to have any of these kinds of coupling, you have to import another class. Of course, in an object-oriented language, this is how you communicate with other classes. Even though it's usually benign, you may want to keep an eye on your import list, and if you see it growing out of control, make some changes to shrink it back to a manageable size. And that's it for this module on component level design. In future modules, we'll talk about other kinds of design like interface design and design patterns. I'll see you there.